All right, so we're going to do guided practice for the 2 reviews for test 4. This may be a long video because that's 2 reviews. Let's do it. Number 1, find the magnitude and direction of the electric field at a distance of 30 centimeters from a point charge of 17.6 microcoulombs. All right, so we're looking for electric field, and it's not constant. We're not between 2 plates, which means we're going to need to use E equals KQ over R squared. Okay, so K is our constant, 9 times 10 to the 9th coulombs constant. Q, we've got 17.6 microcoulombs, so micro meaning times 10 to the negative 6th. And at a distance of 30 centimeters, so that's 0.3 meters squared. Okay, so numerically, we've got 17.6 times 10 to the negative 6th divided by 0.3 squared times 9 to the 9th. Okay, and that is 1.76 times 10 to the 6th newtons per coulomb. Okay, so now when you're looking at your electric field stuff, very often you'll run into these large numbers. That's fine, because it's how many newtons you're getting per coulomb of charge. We've got 17 microcoulombs, but we've got a tiny amount of charge, which means that the actual force being delivered here is also going to be tiny. Okay, so though this is a very large number, the force actually being delivered will be small because the amount of charge is small. Okay, so 2, I guess this would be charge within that field. So like if I put an electron next to this thing, I wouldn't even get a full newton of force, right? Because this times the charge of an electron, charge of an electron's to the negative 16th, okay? So I'd still end up with something to the negative 10th newtons. Tiny, tiny force, okay? So electric fields, large, forces, small. 2, find the electric potential at the position given in problem number 1. So electric potential, that's just another word for voltage, okay? And our voltage equation is just K, Q, over R. All right, another way that we can think about it is our electric field times the distance we're at, okay? Because just multiplying our radius times this KQ over R squared, that just gets rid of the squared. Okay, so these are the same formula. We've already found E, so we just need to multiply it by the distance that it's at. Okay, so multiplying by 0.3. Okay, and we end up with a ton of voltage, 5.28 times 10 to the 5th volts. Okay, so there we go. Next one. 3, find the kinetic energy of an electron that moves from infinity to the position given in problem 1. Okay, so the kinetic energy, let's look at our electrical energy, right? It's K, Q1, Q2 over R. Basically, it's our voltage times the charge that we're putting into it. Okay, so in this case, that Q there is going to be the charge of an electron. Okay, so if we look at it at that position, okay, when it gets to the position in problem 1, right, the radius is the same. Basically, it's just going to be this voltage that we found times the charge of an electron, 1.6 times 10 to the negative 16th. Okay, so that's how much potential electrical energy we have there. Right, we've got negative 2.53 times 10 to the negative 11th joules. Okay, and if we're looking at this formula, right, we got divided by R there. Okay, the larger that R gets, the closer to 0 that electrical potential is going to be. Okay, so out at infinity, R is infinitely large. We're dividing by an infinitely large number, so our UE at infinity is 0. Okay, so it's coming from infinity where it has 0 potential, and it's going to negative 2.534 times 10 to the negative 11th. It is losing potential energy. It's getting more and more negative. All right, so as it loses potential energy, it's going to be gaining kinetic energy. All right, so it lost this much potential energy. That's how much kinetic energy it is going to be gaining. right? In this case, our kinetic energy that it gains as it comes in is equal to the potential energy that it lost. Okay, so that means that our Ke is just 2.53 times 10 to the 11th joules. Okay, it lost that much potential energy coming in, so it's going to be gaining that much kinetic. Okay, 4, find the speed of the electron in problem 3. Okay, so we're looking for speed now. We've got our Ke, right? So if we're looking for speed, moving that kinetic energy formula around, we got Ke equals 1/2 mv squared. So that's going to be V equals 2 Ke over m, and taking the square root. Okay, so 2 times 2.53 times 10 to the 11th divided by our mass. We're looking at an electron coming in, so that's 9.11 times 10 to the negative 31st, and then taking our square root there. Okay, so 2 times, I'm going to do, where did the answer button go? Oh, finger's literally on it. So 2 times that negative answer divided by 9.11 times 10 to the negative 31st, and then taking our square root. There we go. Okay, so we end up with a huge speed. Well, that's impossible. Well, I mean, it might be possible for the question, but it's not possible in reality, because that is, yeah, that's significantly larger than the speed of light. So no, that's not actually going to happen. Anyway, just going with our answer that we got. So 7.46 times 10 to the 3/6/9. Yeah, no, no, that's not. No, that's 25 times the speed of light. What the heck? No, that's fine. For the question, though, we're going with that. Yeah, no. I remember to take the square root. Can I go back? I can't. I just erased it. What an idiot. Okay. Did I remember to take the square root? I think I did. Oh, I definitely did. Okay. Yeah. Wait. That's not the same number. I'm losing my mind. I'm plugging the wrong number somewhere. All right, I'm going to pause for a second. So a couple of screw-ups that I found. On this one, when I did the charge, I used times 10 to the negative 16th instead of times 10 to the negative 19th. So 5.28 times 10 to the 5th times the charge of the particle we put in, 1.6 times 10 to the negative 19th. Okay, so that is going away. So that's going to be 8.45 times 10 to the negative 14th. Okay, and 8.45 times 10 to the negative 14th. Unless I'm making another error, that happens. I'm kind of lazy. So then 2 times that divided by the mass of an electron. And then taking our square root. Well, that's still bigger than the speed of light. Okay. Well, we're going to go with it. You can catch any other errors I made. Congratulations. I'm sure it happened. The actual work, though, like finding our electric field, we're using KQ over R squared, voltage, KQ over R, electric potential energy, KQ over R, and then our speed, taking the square root of 2 KU over M. I may have plugged something else in wrong. I don't know. I'm losing my mind. Yes, we got 4.31 times 10 to the 8th. All right, so it's still faster than the speed of light. I don't know, man. Maybe the numbers I used randomly were a bad idea. Continuing onward. 5. Find the work required to move a proton from infinity to the position given in problem 1. Okay, so we're looking at problem 1. All right, we've got this much electric field. Okay, our voltage, our electric potential, is still going to be that electric field times our distance, so we'll still end up with the same number for that. Our potential energy, so voltage, still the same. Q, it's just going to be a different sign because the Q for an electron, negative 1.6 times 10 to the negative 19th, a proton, positive 1.6 times 10 to the negative 19th. Okay, so the only thing that's going to be changing is that UE is going to be positive close to the charged particle that we're bringing it into. Okay, it is gaining electrical potential by bringing it there. Like we have to add work to move it closer to this charged particle. They're both positive. They don't want to be next to each other. Okay. Actually, you know what? You can still see that. I'm going to go open the blinds real quick so that when that happens again, we can see better. Because I don't want to deal with that. Okay, so blinds are open. Hooray! Anywho, so the amount of electrical potential energy that this thing has close to the particle is going to be the same as an electron had, just in a different sign. Okay, so looking at number 5, the amount of work required to move it from infinity. At infinity, our radius is infinity. We're dividing by an infinitely large number. So that means that our radius is going to make our potential energy go to 0, out infinitely far from this particle, and then we're gaining potential energy, which means it's going to be losing kinetic energy, and we're doing work to move it from one place to another. We have to add energy to get it into this electric field. Okay, so for 5, we already got our number, 8.45 times 10 to the negative 14th. Just going to really quick make sure I didn't make some other stupid mistake along the way. Just go through the whole thing again. Yep, that's fine. And then times 0.3, hooray, that's fine. And then times 1.6 times 10 to the negative 19th, that's fine. Yeah, okay. Yeah, so this is the amount of energy that we need to add to get it from infinity into this point, the amount of work that we need to do to give it that potential energy that it has. Okay, so finding the electric potential energy in problem 5, well, that's what it has. That's it. We did work to add potential electrical energy. It's like raising something off of the ground. Instead of adding gravitational energy, though, we're adding electrical potential. All right, you are moving something through a field. Next one, number 7, find the speed of the proton in problem 5. It is allowed to accelerate away to infinity, so it has this much electrical potential energy, and then as it moves away from the charged particle, it is going to be losing potential energy and gaining kinetic energy. If we go out to infinity, our electrical potential energy is 0, which means that all of that energy has gone into kinetic energy. So this is Ke. All right, so it's honestly going to be almost exactly like this. The difference being we have a larger mass. Okay, so you've got 2 times 8.45 times 10 to the negative 14th. Okay, and our mass is instead, oh God, 1.67, 1.27. I've got too many constants in my head. I always forget. Hold on, just one sec. 1.67. Fantastic. 1.67 times 10 to the negative 27th. Okay, so now plugging and chugging, we've got 2 times our answer from our last one divided by 1.67 times 10 to the negative 27th, taking the square root, and oh, well, that's a much more reasonable number. Yeah, look at that. Under the speed of light, look at you go. So we've got 1.01 times 10 to the 7th meters per second. So still going very fast, but at least it's not breaking the rules. Okay, so now we got number 7. Number 8, a capacitor has a capacitance of 25,000 microfarads and is attached to a 1,200 volt supply. Find the charge stored on the plates. Okay, so we've got capacitance equals charge over voltage. Okay, we're looking for the charge stored, so we're just going to be multiplying V over. So Q is going to be equal to our capacitance, which is 2,500 microfarads, so 2,500 times 10 to the negative 6th, and times our voltage of 1,200. There we go. So 25,000 times 10 to the negative 6th times 1,200, and that's just going to be 30 coulombs. Yeah, just 30 coulombs. That's a huge amount of charge. Okay, next one. Number 9, find the energy stored in the plates from problem 8. Okay, so we're looking at energy. Yeah, that's number 9. So our way of thinking about electrical potential energy, if you've got a constant voltage, is just our charge times our voltage. All right, that does not work for capacitor, because as you're adding charge to it, you need more and more voltage to continue putting new charge on. All right, if you were to graph it, you would end up seeing that sort of shape. So looking for the area underneath there, which is energy, we've got half of that, because you're finding the area of a triangle instead of the area of a rectangle. Okay, so that's going to be 1/2 V times Q. Okay, so that's 1/2 1200 times 30, so that's just 1200 times 15. Okay, and we end up with 18,000 joules. There we go. Number 10, find the capacitance of a capacitor with a charge of 6 coulombs and a voltage of 12 volts. Okay, so that's just going to be 0.5, right? Because we got capacitance equals charge over voltage. We've got a charge of 6. We've got a voltage of 12. Yeah, it's 0.5. 0.5 farads. Okay. Number 11, find the potential difference across a capacitor with a capacitance of 5 farads and a charge of 2.5 coulombs. Okay, so we're looking for voltage now. Okay, so our voltage would just be Q over C. So we've got a charge of 2.5, we've got a capacitance of 5, so 2.5 over 5. We again end up getting 0.5, this time volts. Number 12. Find the charge stored in a capacitor which has a voltage of 24 volts and a capacitor, or a capacitance of 6 farads. Okay, so looking for charge, that's just multiplying our voltage over. So this is going to be 24 times 6. I don't want to think at all. No. Oh my God. Come on, man. All right, so we got 144. 144 coulombs. All right. For the capacitor in problem 12, find the number of electrons which were removed from the positive plate while the capacitor was being charged. All right, so we've got this much charge here. Okay. Each proton, what is it, protons? Electrons? Yeah, each electron. It doesn't matter either way. Each electron has a charge of 1.6 times 10 to the negative 19th. So if we've got this much charge and we want to find out how many electrons we've got, we just need to divide that by the charge of an electron. It'll tell us how many electrons were removed. So 144 divided by 1.6 times 10 to the negative 19th. And that took 9 times 10 to the 20th electrons. Go us. Look how many electrons we're taking off for that truly obscene amount of charge. 14. An electrical field of 10,000 newtons per coulomb exists at a certain distance from a point charge. What will be the electric field if the distance from the point charge is tripled? So if we're looking at our electric field formula, we've got this E equals KQ over R squared. Okay. So if we are increasing our radius, it's obviously going to have an inverse relationship to our field, but because of that squared there, like if I doubled my radius, right, I'm now dividing by a number that is 4 times as large because I've got 2 squared. Okay, if I triple my radius, I'm now dividing by a number that is 9 times as large because I've got 3 squared. Okay, so it's an inverse square relationship. All right, if I triple my distance, I will end up with a 1/9 of my electric field. All right, I don't know what Q is. It doesn't matter. I don't know what R is. It doesn't matter. It's the relationship that's happening. It's an inverse square relationship. If I increase my radius, my field will go down by that amount squared. Okay, so this one starting off with a field of 10,000 newtons per coulomb and just dividing it by 9 because we are increasing this distance by 3, so dividing by 3 squared. Okay, so I end up with 1,100 newtons per coulomb. That's not a C, dummy. There we go. Better. 15. The electric potential of 500 volts exists at a certain distance from a point charge. What will be electric potential at the distance of the point charge is tripled? So with voltage, we've instead got KQ over R, no squared. Okay, so because there isn't a squared there, it's just an inverse relationship. It's not an inverse square relationship. So as you triple your radius, it's just going to cut your voltage by 3. Right, so 500 over 3, we end up with 167 volts. All right, got cut into thirds. Okay, no squared in the formula, which means you don't need to square the change. 16. An electrical field of 10,000 newtons per coulombs exists at a certain distance from a point charge. What will be the electrical field at the same distance if the charge of the point charge is tripled? All right, so looking up at this one, all right, Q is on the top of that thing. It's in our numerator, so as Q gets larger, our electrical field will get larger. All right, also because there isn't a squared or any other exponent on there, it's just a straight up direct relationship. Okay, so as we increase our charge, our electric field will increase directly. Okay, so tripling our charge will triple our electric field. Okay, so that one will just end up being 30,000 newtons per coulomb. Okay, so main thing to be careful with is with electric field and electric force, if you're changing your radius, it's an inverse square relationship. Okay, so if you double it, divide by 2 squared. Triple it, divide by 3 squared. Multiply it by 5.993. Divide your electric field by 5.993 squared. Okay? It's always squared, inverse square, if you're dealing with electric field and electric force. Voltage and electric potential energy do not have an R, like an R squared. It's just an R. It's just an inverse relationship. They don't follow the inverse square. Okay? Number 17, a charge A is 9.6 microcoulombs. Charge B is negative 3.2 microcoulombs. We're looking for the net electric field at point X. Okay, so we're basically just using E equals KQ over R squared twice. So if we're doing it for our first one, we've got 9 times 10 to the 9th. We've got Q of 9.6 times 10 to the negative 6th. And we've got a radius of 0.2 meters squared. Okay, so our first one, we've got that. Okay, so there's A. And it's a positive number, which means that this field is repelling away from A. It's pointing in that direction. Okay, for B, we've got K, Q, our Q is 3.2 times 10 to the negative 6th, and our radius is now 0.09 squared. Okay, so for that one, we've got 3, 5, 6. Yeah, 4. Okay, so we've got our two numbers. All right, and this one, because it was a negative charge that we plugged in, is going to be giving us a negative field, which means an attractive field. It is attracted to B. All right, so A is pushing it to the right, B is pulling it to the right. But these two fields are in the same direction, which means that if we want to find our net field, we're just going to be adding the magnitudes of these two together. Okay, they're both pointed the same way. All right, so we're just going to be adding our field from A to our field from B, and we end up with 5.72 times 10 to the 6th newtons per coulomb. Okay, so when you're thinking about the signs on here, remember that they're on different sides, right? So positive means repulsive, negative means attractive. I would physically draw the arrows on the page just so you don't get mixed up as to which way things are going. B, find the net electric potential at point X. Okay, so electric potential, that is just our voltage. Okay, so V, KQ over R. I mean, we've got those two values up there, so we can just do 216,000 times our distance of 0.2. Okay, so we've got 4.32000. Okay, and then for our other one, 3555555 times 0.09. And now we've got those two. And again, these things are pointing in the same direction, so we're just going to put them together. All right, so our net voltage there, 7.52 times 10 to the 5th volts. There we go. Fantastic. Find the work required to move a proton from infinity to point X. Okay, so moving it from infinity to point X, we've got this positive voltage here. So looking for our electrical potential there. Right, we're just going to multiply by charge of an electron, right? Because we got UE equals QV. Okay, so this is the amount of electrical potential energy that it has when it's brought to X. Okay, it doesn't want to be there. We have to do work to add it there. Okay, and if it's out at infinity, right? At infinity, your radius is infinitely large. So dividing by an infinitely large number to find that electrical potential energy, we end up with no electrical potential energy. So it's gaining all this electrical potential energy when being brought in, and it's gaining it because we're doing work. Okay, so C is just the amount of electrical potential energy that it has there. 1.20 times 10 to the negative 13th joules. Okay, and then screw it. We're just gonna do D right here. This is C. Find the final speed of the electron, which moves from infinity to point X. Okay, of an electron. Okay, there we go. So we've already got our electric potential energy, and thinking about an electron, all right, the only difference is the sign of this would change. So it's starting with negative potential when it's in this area here, all right, and it is moving from infinity. Out at infinity, you've got no electrical potential because your radius is infinitely large. Okay, so that means that this is the amount of kinetic energy that it would be gaining coming in from infinity to that point. Okay, so we've got KE. Okay, so now looking for V, that's going to be the square root of 2KE over N. Okay, so 2 times our answer divided by 9.11 times 10 to the negative 31st, the mass of an electron, and then taking the square root of that, we've got 5.14 times 10 to the... Again, we end up with 1 going faster than the speed of light. Blame Jennings. I got these numbers from him. I'm a thief. Anywho, there we go. So, number 18 now. This is the last one for review number 1. 18, charge A is negative 9.6 microcoulombs. Charge B is 6.0 microcoulombs. Find the net electric field at point X. Draw a vector diagram. Okay, so we've got point X right there. All right, let's look at charge A first. Okay, so charge A, we've got, well, we're going to be doing the same formula we used on the last one, where our electric field is KQ over R squared. Okay, our Q, screw it, let's just do the whole thing. So 9 times 10 to the 9th times our charge of negative 9.6 times 10 to the negative 6th. Okay, and then divided by our radius squared, so we're 4 centimeters away, so that's 0.04 squared. Okay, so this first one, we've got a field of negative 5.4 times 10 to the negative 7th, and this is from A. Okay, so a negative field means an attractive field. Okay, so if we're looking at just the field being produced by A, it is trying to pull anything in position X to the right. Okay, and it's pulling with an electric field of 5.4 times 10 to the, no, not, oh my God. Haha, there we go, 10 to the 7th. Okay, so we've got that field there. Our other field, using 9 times 10 to the 9th, times our other charge, which was 6 times 10 to the negative 6th, divided by our distance there of 0.02 squared. Okay, so this one, because it is a positive charge, it will be repelling things away from it. Okay, so this one will be pointing downward. Okay, so for this one, we've got 1.35 times 10 to the 3/6 eighth. So clearly not to scale. There we go. So we've got our 2 vectors there. All right, if we're looking for our net electric field, it would just be the sum of these 2, which means the hypotenuse of a triangle really would have been better if I had planned ahead and not written a number right where I was going to draw it. It's fine. It's fine. It's fine. It's fine. So we're looking for that hypotenuse there, which means we need to use Pythagorean theorem. So squaring our 2 sides and then adding them together and taking the square root. Okay, so we end up with a net electric field of 1.45 times 10 to the 368 newtons per coulomb. Coulomb, not 6. Jeez, my handwriting's terrible. There we go. Cool. And it is larger than either of those two and smaller than the sum, so things check out. Go us. So that was A. B, find the acceleration of an electron at point X. Okay, so we've got our electric field. All right. One thing that will be useful to us if we're looking for the acceleration is the amount of force. So electric force is just your electric field times the charge of the particle that you're putting in, so times the charge of an electron. Okay, so 1.45 times 10 to the 8th times 1.6 times 10 to the negative 19th. Okay, so this thing is exerting a force of 2.33 times 10 to the negative 11th, which seems real small. Okay, but we're not looking for force. We're looking for acceleration. Okay, so we're going to be using F equals ma. Okay, we've already got our force. We just need to divide by the mass of an electron, so that's 9.11 times 10 to the negative 31st, and we end up with an acceleration of 2.55 times 10 to the 19th meters per second squared. Voila. And we got it. Woo! There's number 1. Let's do our second one. Where did I put it? There it is. Okay. So looking at our second review for test 4, what is the charge and mass of an alpha particle? Okay, so an alpha particle is just a helium nucleus. So helium is made of 2 protons and 2 neutrons. So mass-wise, this thing is just going to have a 4 times the mass of a proton, because protons and neutrons are basically the exact same size. Okay, so if you've got the the mass of a proton, that'd be 1.67 times 10 to the negative 27th. Just multiply it by 4. And there's its mass. Charge-wise, neutrons don't have any charge, so it just has the charge of the 2 protons, each of which have the elementary charge. So it's going to be 2 times the charge of the elementary charge. Okay? Number 2, a conducting sphere has an initial charge of negative 4.8 microcoulombs. How many electrons must be removed from the sphere so that it'll have a net charge of 9.60 microcoulombs? Okay, so let's just look at how much it changed by. So our final charge minus our initial charge. Oh my God, 9.6 minus a negative 4.8. Why did I just add it? So we have removed 14.4 microcoulombs of charge. Okay, so let's just. Oh my God. Great. So we've got the amount of charge that we've moved. Okay, and we're looking for how many electrons must have been removed to create that charge. So each electron has a charge of 1.6 times 10 to the negative 19th. So if we're looking at this total charge that we've removed, well, we just need to divide it by the charge of an individual electron. That'll tell us how many electrons we have. Okay, so divided by 1.6 times 10 to the negative 19th, and we end up with 9 times 10 to the 13th electrons. Voila. Cool. Number 3, a conducting sphere with a net charge of negative 6 microcoulombs is brought in contact with another conducting sphere of the same size, which has a net charge of positive 2 microcoulombs. What is the charge on each sphere after they have been brought into contact? Okay, so total charge-wise. All right, we got negative 6 and a positive 2. When they come together, some of that's going to cancel out. Okay, so negative 6 and a positive 2, add those two together, and you've got a negative 4. All right, now if you're looking at these conducting spheres, they're the same size and they're conducting spheres. So on a conducting sphere, each of these electrons is going to try and get as far away from each other as possible. They're going to spread out evenly. Okay, so if we've got a total charge of negative 4 microcoulombs, yeah, negative 4 microcoulombs, and spreading out evenly, that means that each one of these spheres is going to get half. Okay, so that means that each sphere, splitting up our negative 4 microcoulombs, each one's going to get negative 2 microcoulombs. And there's our answer. Yay, I didn't have to break out the calculator. 4, the radius of the spheres in question 3 is 0.15 meters. What will be the electric field at the surface of one of the spheres after contact? Okay, so we're looking for electric field, which means you can use KQ over R squared. Okay, so K, 9 times 10 to the 9th, Q, negative 2 microcoulombs, and our radius, 0.15 squared. Okay, so we've got negative 2 times 10 to the negative 6th divided by 0.15 squared times 9 times 10 to the 9th, and that gives us an electric field of negative 8 times 10 to the 5th newtons per coulomb. Cool. Wow, that was a terrible circle. Number 5, what will be the magnitude of the electric force on a proton at the surface of the sphere in question 4? All right, so if you're looking for force, that's just going to be your electric field times the charge that you're putting inside of that electric field. So we're looking at a proton, so we're just going to be multiplying this by charge of a proton 1.6 times 10 to the negative 19th. Oh my God! There we go. All right, so that's going to be 1.28 times 10 to the negative 14th newtons. Hurrah. Number 6, what would be the electric field from the sphere in question 4 at a distance of 0.075 meters from the center? So each of these spheres is 0.15 meters wide. If we're only 0.075 from the center, that means that we are inside of this conducting sphere. If you're looking at an electric field inside of a conducting sphere, right, conducting sphere is building up all of that charge around the outside, and it's uniformly distributed around a circular sphere. Mine is a little lumpy. That's okay. Okay, so if I'm at a point inside of this thing, doesn't matter where I'm at, if I'm over here, okay, these electrons spread out over here, they're close by, they're negative. There's going to be a larger attractive force to those because I'm closer to them. Okay, but I've got significantly more electrons on the opposite side. They're further away, but there's more of them. All right, so they're going to have a smaller electric field, but there's so many more field lines being made because there's more charge over there. All right, if you add it all together, it's always going to end up canceling out. All right, you're closer to this side, but there's more charge over here. Right, because it's spread out over a sphere, it ends up canceling out perfectly. Okay, so the charge or the net electric field inside of a conducting sphere is 0, no matter where you're at. All right, it's easiest to see where it's directly at the center because then all the vectors are the same size. But no matter where you're at inside of a conducting sphere, your net electric field is 0. Okay, 7. An electron and a proton are 10 centimeters apart. Find the electric force on the proton. Okay, so electric force, that's just using Coulomb's law. F equals K Q1 times Q2 over R squared. Okay, I got an electron and a proton, so that's going to be 1.6 times 10 to the negative 19th, squared. Because each of those charges are the same, it's just one's negative, one's positive. Divided by our radius, so 0.1 squared times 9 times 10 to the 9th. Fantastic. So we've got a force on the proton, an attractive force of 2.3 times 10 to the negative 26th newtons. Okay. B, well, we've got the same charge 1, same charge 2, same distance between them, same K. So that means this one's also going to be the same force. Right? You got equal and opposite forces between things. Right? It's like the gravitational pull of the moon compared to the gravitational pull of the Earth on each other. It's going to be the same. Okay. The acceleration of the electron due to the electric force. Okay, so now using F equals ma, taking this force and dividing by the mass of an electron, so divided by 9.11 times 10 to the negative 31st, and this thing ends up getting an acceleration of 2.53 times 10 to the 4th meters per second squared. It's booking it. Okay, D, acceleration of the proton do this. All right, so starting off with the same electric force, 2.304 times 10 to the negative 26 divided by 1.67 times 10 to the negative 27th. Hooray. This one, significantly smaller acceleration. We've only got 13.8 meters per second squared. Not going so fast. Okay. E, gravitational force on the electron. Okay, so looking at gravitational force, very similar formula, except instead of a K, you've got a big G, and instead of charges, you have masses. So M1, M2 over R squared. Okay, so gravitational. So that is 6.67? Yeah, 6.67 times 10 to the negative 11th times the mass of 1.67 times 10 to the negative 27th times 9.11 times 10 to the negative 31st. So we've got our mass of our proton, mass of our electron, divided by our radius squared, which is still 0.1 squared. Wow, that number's minuscule. Gravity sucks. Gravity's not strong. That's okay. Look at that. Look how tiny that number is. Well, I mean, this was a tiny number too, times 10 to the negative 26th, but times 10 to the negative 65, minuscule. Gravity is extremely weak compared to electrical fields. That's not the right letter, is it? Oh, I thought that was a C. I can't even read my own handwriting. There we go. E. F. There we go. Gravitational force on the proton. Hey, look, it's the same values that we just had in E. So, yeah, they exert the same gravitational force. They exert the same electrical force. Just in opposite directions. 8. Object A has a charge of 3 microcoulombs. Object B has a charge of negative 2 microcoulombs. The distance between the objects is 5 centimeters. Point X is halfway between the objects. Point Y is 2.5 centimeters from object B. Find the magnitude and direction of the electric field at point Y due to charge A only. Deal. So our electric field is just going to be K times Q over R squared. I feel like we've done this one before. You know what? I believe in you that you can calculate these things. Let's just talk about the direction of which way they're going. So charge A is a positive 3 microcoulombs. Okay, so that means that at point X, it's going to be pointing that way. Okay, at point Y, it's still going to be pointing that way. Okay, but when you're at point Y, this field is going to be significantly smaller, right? Because if this is 2.5 centimeters, another 2.5 centimeters, another 2.5 centimeters, we have tripled the distance to get out to point Y from point X. So that means that our field at point Y from charge A is going to be 9 times smaller. It actually can help us cut down a little bit on calculations. You've got that inverse square law. You don't need to worry about plugging in all your numbers. Your field at Y is just going to be 1/9 of what it was at X. Okay. Now when we're looking at B, you've got a negative 2 microcoulombs. Okay. So over at point X, it's going to be pulling towards B because B is negative. Okay. At point Y, well, towards B is now the opposite direction because we're on the opposite side of B. Okay, so when you're looking at the net field at point X, they're both pointing the same direction. So you're going to add those two magnitudes together. Okay, when you're looking at point Y, they're now pointing opposite directions. So you would subtract one from the other. Right, B is going to be our larger one because we're significantly closer to B. Okay, so just subtract A from B, and there's your net electric field. Oh, hiccuping. Okay, so when you're looking for those, you can expedite it a little bit, right? When you're looking at the electric field from charge A at point X compared to point Y, at point Y it's going to be 9 times smaller because it's 3 times further away. The electric field magnitude is going to be the same for charge B at both X and Y because of the same distance away. They're just pointing opposite directions. Okay, when you're looking for your net field at X, add the two vectors together. When you're looking at your net field at Y, subtract them. Okay. 2 identical 0.005 kilogram balloons hang from threads which are 25 centimeters long. The distance between the balloons is 15.5 centimeters. Both balloons have the same charge. Find the magnitude of the charge on each balloon. Now, remembering walking through this with some people, I did this in a dumb order. Actually, Jennings did this in a dumb order. I stole it from him. Or maybe he did it in a very smart order that makes people think through the entire thing and then they realize, oh, I already found all of that along the way. Who knows? Who knows the method behind his madness? Who knows the method behind anyone's madness? Continuing. 9a. Looking for the magnitude of the charge. Okay, so if we want to find the charge, that means we're probably going to need to find the electric force. All right, because we've got Fe equals K Q1 Q2 over R squared. Okay, luckily these two charges are the same, so what we've effectively got for this particular problem is that we've got KQ squared over R squared, because those two charges are the same. We've got R, we've got the distance between them, we've got K, we're looking for Q, we do not have Fe. Okay, but solving this through, we would just do Fe times R squared over K, taking the square root. Okay, so there's our formula for Q once we've got our electric field. Now looking at this problem, all right, we've got a distance here, we've got a distance here, right, which means that we could find like the angle of this triangle if we wanted it. We also have a mass, okay, which means that we can find our weight, okay, which you're actually going to have to do for B. So let's handle B. All right, B, FW equals mg. Okay, so you've got 0.0050 kilograms times 9.8. Okay, so we can find our weight super easy. Okay, and our weight will be helpful to us because we're going to need it for part A because we need to find some vectors. All right, C, the angle of each thread. Okay, so we've got a hypotenuse of 25 centimeters, and we've got a opposite side of, I don't want to think, what's 7.5, so 7.25? Yeah, 7.75. Ah, stupid. So we got 7.75 along that opposite side. Okay, so we can find our angle by just using SOHCAHTOA, right? We got opposite, we've got hypotenuse, so the sine of that angle is equal to 7.75 divided by 25, all right? We're looking for theta, so then you just take the inverse sine. Fantastic. Okay, so we can find that angle. Make sure you're in degrees. And we can find our weight. Okay, so now we could go back to this. Go back to this finding our electrical force. Okay, because if we're looking at that triangle, right, once we've got our angle in there, once we've got theta, our weight is that adjacent side. Our electrical force is that opposite side. Okay, so if we're looking for FE, right, we've got opposite, adjacent, and angle. Okay, so that means we're going to be using tangent. So the tangent of our angle equals opposite over adjacent. So solving for that opposite side, we're just going to be multiplying that adjacent side over. So it'll be the tangent of our angle times our weight. And that will get us our electrical force. Doesn't matter which side of this triangle you're doing, it's symmetrical. Okay, so that'll get us the force here, and then we can plug that back in, multiply by our radius squared, divide by k, and take the square root, get all that happy trash out of the way, and there's your Q. Now looking for the tension, that's looking for the hypotenuse. All right, so you can use any trig function that involves your hypotenuse in it. You can use Pythagorean theorem because you've got the two legs of your triangle. It's entirely up to you. You do you. And we've already drawn that diagram basically, because if we're looking at this charged particle, right, you've got your weight going down, and you've got your electrical force pulling it to the left, pulling it away from the other one, and you've got your tension canceling those two out, pulling up and to the right. Okay, not going to worry about finding the numbers on that. I believe in you. Also, I'm tired and hungry. So, yeah, that's it for the video. All right. It was a little bit less chaotic than the last review. I only had a couple of brain farts at the beginning and a couple of particles going faster than the speed of light. That's fine. That's fine. No problem with that. So, yep.